Okay, so we're officially in Unit 2. We're going to start with the tangent line problem. I'm going to ask you to pause the video every now and again, try some of the problems, and then restart the video so you can try some of these on your own. So once we get started, we'll start right away by pausing the video because I want you to fill in the do now before you continue. So I'll give you a second to pause, try the do now, and then come back. So this is what I put in. You don't have to have verbatim what I have, but a secant to a circle is a line that intersects the circle at two distinct points. And I drew a picture. And the tangent line is, or the tangent to a circle is a line that touches the circle. And I like using the word touch because it has a similar meaning. Tangible is also touch, and that's where the name tangent comes from. So touches the line and exactly 1 point. And I added in here, it's perpendicular to the radius of the circle at the point of tangency. Now, you didn't have to have that exactly, but I just thought it was interesting and added it in. So this part here is not required. Now we need to look at, because for a circle, it's kind of obvious. It could just, some people in geometry say, oh, it's the line that intersects a circle in exactly 1 point. But I would rather think of it as a touching more than anything. So I want you to look at, because these are also considered tangent lines down here at the bottom. In calculus, we then expand the idea of what tangency means. So I want you guys to look at these 3 examples and see if you can come up with another definition, because clearly on the rightmost function, you can see the tangent line intersects the curve in more than one place, but it's tangent at those points that are plotted for us. So try and think of an alternate definition. Pause the video, and then once you've thought it, write it down, and then you can even go and look it up if you like. Here's one of the more simple definitions that I found that is very descriptive. A tangent line is a line which locally, the key word here, oh, I have to circle it on my iPad, is locally touches the curve at one and only 1 point. Also, some definitions discuss parallel, that it's parallel to the curve, because if you zoom in close enough, it's just touching, so if it makes it look like they're almost the same line or that they run parallel to each other. That's a rare form of definition for it, but I have seen it out there. But the key is that it touches in exactly 1 point locally. It could intersect in other places on the curve, but just in the local area where we're talking about the point of tangency is what we're concerned about. So what are some of the things we need to write the equation of that line? Because the tangent line becomes super important, especially in calculus. That's one of the main, like almost half of the year kind of revolves around the slope of the tangent line and things like that. To write the equation of a line, you need 2 things at a minimum. So I want you to pause the video, or if you could do it quickly, put it in right now. So the 2 things we needed to write the equation of a tangent line, we need to find the slope, sorry, I'm looking at my iPad here, and a point. Now, if we're talking about tangent lines, usually you have to be given the point of tangency, so that part is there already. So really the hardest part of these type of tangent problems is finding the slope of the tangent line so that we can do that. Now, we don't know what the slope of the tangent line is, but we can find the slope of a secant. So we're going to use that idea of a secant to help us do that. So most of the work will be concentrating on finding the slope of the tangent line. We can approximate it using the secant. A secant line is a line through a point of tangency and a second point on the graph. I'm going to name one of the points point P, which is some constant value, at some constant value C, and the corresponding Y coordinate is f of C. And then we're going to do some change to X. It could be 1, it could be 0.1, it could be whatever size we want to give us point Q. So we are going to use this secant line to help us approximate, since we can't find the slope of the tangent line or find actually what the tangent line is without having some idea of what the slope is. So we're going to kind of try and finagle the system a little bit by finding the slope of the secant line. So remember, the slope of the secant, or the slope of any line, is the change in y over the change in x. So I want you to try to write down the slope of the secant line. I left some space over here to do that. And I'm going to pause the video and put my answer in. So pause and then come back. So far, just a side note here, we want the slope of the secant line. I am using notation to indicate that it's just the slope of the secant line. It's the change in y over the change in x. I'm going to take the two y values, the y value for the q, which was f of, oh, I have a typo in here, I can see. This needs to be a C there, and that needs to be a C there. So if you could fix that, that would be great. C and C there, like that. So it's going to be f of C plus delta x minus f of C over C plus delta x minus C. So I'm changing, it's the change in y, so I'm subtracting the two y values and then subtracting the two x values, which then becomes f of C plus delta x minus f of C over, and the two c's in the denominator cancel out, we get delta x for the slope of the secant there. All right, moving on. Imagine you can move the point Q closer to point P. So what I want you guys to think about, here's my point Q up here. If I took that point Q and started moving that closer and closer to point P, that means my delta x would get smaller and smaller and smaller. What would happen as point P moves closer to point, I said point P, I meant as point Q moves closer to point P, what's the relationship between the secant line and the tangent line? And the way to explore that at the point of tangency, the way to help us answer this is we're going to draw in some secant lines. So I want you to draw at least 4. When I did this earlier, I was able to fit in 5 of them, but if you can at least fit in 4, and you pick where you put them, I'm fine with wherever. So now we have I have 5, you may have 4. What I'm hoping that you see is as Q moves closer and closer, your tangent line, or your secant line, approaches the tangent line. So that's what we're going to write down here. It says, it's asking what's the relationship. The secant approaches the tangent. So if we think about that, complete the sentence as delta x approaches 0. That means that Q essentially is moving closer to P. The slope of the secant line, finish that sentence. The slope of the secant line will approach the slope of the tangent line. So what can we use to move the second point Q, infinitely close to point P? Because if it's approaching the tangent line, if I can get it delta x to be infinitely small, that means I can get and approach the slope of the tangent line, or can find the slope of the tangent line. So what in the last unit did we learn about to help us with this problem? I'll pause it and you will write down the answer. I am hoping you wrote limits of some kind. So now let's apply that here. It says try writing an expression to find the slope of the tangent line. So I'm going to write here slope of the tangent line equals, and then you're going to try this on your own. The answer is actually on the next page, but give it a shot and see if you can figure it out on your own. You're definitely going to use the slope of the secant line, but apply a limit to it. Let's see how accurate you can get, and then you can scroll down to the next page to check your answer.